Hello everyone. With this video, we are going to start a new module called as Design Theory for Relational Databases. So in this module, we'll cover the basics of functional dependency theory, and we will talk about normalizations like BCNF and 3NF, and then we'll also talk about some algorithms to decompose a relation so that the end result is in so either 3NF or BCNF, right? So just to give you a quick motivation, why do we need this chapter is that this chapter is more of it lays down some fundamental theoretical knowledge on basis of which you can if you design your tables, then they are guaranteed to have some nice properties, right? So far, when you were studying the ERD model, that module, then we always went with an intuition of what should our tables be, right? We went through the business logic, and then we sort of brainstormed, and we thought that probably this is the best way. We drew an diagram, and then sort of converted the entities and relationships into tables for our schema, right? So that was more of an intuition driven thing. So here we are going to go little bit more theoretical in our approach for designing tables and schemas. So the key thing over here is something called as functional dependencies, right? So of course, and the irony being that these functional dependencies, they are actually derived out of business logic, and then using these functional dependencies, we'll lay out a very formal approach towards designing your tables, right? So let's get started with the definition here. What is a functional dependency? So functional dependency is any assertion like x implies y that holds on your relation, right? So it basically means that whenever I say x implies y, I say that on my relation R, whenever two tuples agree on all the attributes of X, then they must also agree on all the attributes of the Y, right? So here, bit of a notation that I'm going to use in the slides is that both X and Y, whenever I use X and Y, they can be a single attribute or they can be a set of attributes also, right? So whenever I say x, it does not mean that it's just a single attribute. It can be a bunch of attributes also. And when we have only individual attributes, then we talk about them using these alphabets a, b, c, d, and all that, right? So just a notation which is being followed in these slides. By the way, before we go forward, I should mention this, that these slides, I took them from your textbook author, and uh, they are okay, but by no means these slides are a substitute to your actual textbook, right? So your textbook is very nicely written. For this module, you should be reading the Ullman's textbook. Okay, so let's continue here. uh, so as I was saying that whenever we have an functional dependency, and we write the functional dependency as a set of attributes implying another set of attributes, right? So whenever we write something like this, I mean that uh, if two tuples in my relation R have same values for all the attributes on the left side, then they will also have same values for all the attributes on the right side, right? So just to give you some classical examples, so let's say if you are designing an student relation, your x a functional dependency could be that student id or roll number. So given a roll number, it automatically implies that about his CGPA, or name and age and so on, right? So that is one example. Another example could be that let's say you are booking, you're making an application for railway reservation system. Then your X could be that given a train number, and date, and maybe coach and berth number, you need uniquely identify who is the passenger that is going to sit on that berth for this particular date, right? So these are the kind of examples about functional. You can derive a lot more. We'll also see some examples here. Okay, so that's the functional dependency, the definition of functional dependency, right? So yeah, so I think we have covered these definitions of super key and key multiple times, but using functional dependencies, we can truly define what is an super key and key, right? So we define the super key for a relation R. Right? So K is a super key for a relation R if and only if K functionally determines all the other attributes in relation R. So this is the most formal definition that you can have for super key, right? So of course, we have defined super key earlier also when I was teaching SQL and all that. But note that this definition is not in conflict with the ones which I have already covered. I'm just putting it more formal, and so that's the super key. And key, as always, we define it as it is a super key which is minimal in size. Okay, so that means it's an super key such that no proper subset of a key can be a super key, right? So this other way of saying this is that this, if k is minimal in size, then it is called as a key. Otherwise it is called as a super key. Okay, forward. Okay, so the way we are going to cover this set of videos is that first I'm going to talk about functional dependencies and some properties of functional dependencies, some kind of mathematical properties of functional dependencies. And then we'll cover some basic things like projection of functional dependencies and all that. So once the basic things are covered, then we'll go into normalization, because the normalization, that set of slides will actually use this functional dependency theory. Okay, let's start. Okay, so some properties of functional dependencies. So let's say you have a functional dependency like this: x implies a1, a2, and an, right? So here, as always, I'm saying that x may not be one attribute; it can be more than one attribute also in this particular set of slides. That's the notation which I'm following here, right? So this x can be like c d e f. It can be a set of attributes, right? So whenever you have an functional dependency like this, then it can be broken down into these functional dependencies. In other words, this is called as splitting of the right sides, right? So an example is that if A implies B and C, it is equivalent to saying that A implies B and A implies C, right? Just take a simple example, right? If your A attribute is student ID, right? So student ID can uniquely identify both your name and CGPA, right? So either you write it as two functional dependencies, that student ID implies your student name, and student ID also implies its CGPA, or you can say that given a student ID, I can uniquely identify the pair of student name and CGPA, right? They are mathematically same. That's all I'm saying, right? Okay, so this is called as the splitting rule of the right side. Note that there is no splitting rule on the left side. So that means if you have an functional dependency like given train number and date of journey, I can uniquely determine the number of sleeper coaches. Let's say that that is a functional dependency. I cannot break the left side of this functional dependency. I cannot say that given a train number, I can uniquely identify the number of sleeper coaches, because the number of sleeper coaches may be different. across different dates, because the admin may decide that there isn't much business, so maybe he can reduce the number of sleeper coaches on weekend or something like that, right? So moral of the story is that if you have any FD like this, you can trivially break it into two FDs where the right side is only one attribute, but you can never do that for the left side. If I had a functional dependency like AC implies D, I cannot say that A implies D and C implies D until unless you do some actual deduction and prove. In your set of FDs it may still be true, but it does not hold always. You'll have to be very careful. That's all I'm saying, right? Okay, next rule. This is called as trivial functional dependency, right? So here, I'm just taking a snapshot from your textbook because it's so nicely written there. So it says that in any relation, we FDs of the following form. Let's say you have a set of attributes here, A1, A2, AN, and then it say that it implies B1, B2, Bm, such that the right side is always an if the right side is a subset of the left side, that means B1, B2, Bm is a proper subset of it's a subset of your left side, A1, A2, AN, right? If this is the case, then this functional dependency is always trivial, right? So you can think it this way, right? Let's say you have train number and train name, right? Yeah, train number and train name will uniquely determine the train number, or given student name and student ID, it will uniquely determine the student name, right? So these all are trivial. So whenever the right side, if the right side is the subset of the left side, then it trivially holds. That's all I'm saying, right? So this is what is called as trivial functional dependency. Forward. Transitivity rule, right? So I think you must have studied about this in your discrete math also. Let's say there is a relation where the following two functional dependencies hold. So you have a set of A's here. This implies B1, B2, Bm, and then B1, B2, Bm also implies C1, C2 to Ck, right? So if you have something like this, then A1 through An will imply C1 to Ck. A simpler way to think is that if A implies B and B implies C, then the functional dependency A implies C will also hold in your relation, right? So it's very intuitive. I don't think I need to cover this more deeply. Okay, so next we, just a slide on something called as Armstrong rules, right? So Armstrong rules, they are nothing but, they are just a collection of simple FD inference rules. So first is the reflexivity. That means, if the right side is the subset of the left side, then it trivially holds. And then transitivity, you also know that. And then there is something called as an augmentation rule. That means if you have an FD like this, A1 through AN implies B1 through BM, then if you add some set of attributes onto the left side and the same set of attributes onto the right side, then this will hold, right? So this is called as the augmentation rule, right? So the property that these three have is that, right? So Armstrong rules, they says that we, if we want to know if any particular FD holds or not, we can always use reflexivity, augmentation, and transitivity in a creative way to check if a given FD is, if it can be inferred from the other FDs or not. Right. So this is one way of doing it using Armstrong rules. We'll cover several ways, but let me just give you an example here. Right. So let me change my slides for just a little bit. Okay. So now I'm changing my slides. These slides are from your Silber, Schatz and Korth's textbook, but I think they do a good job when it comes to talking about Armstrong rules, right? So you know sorry for this, but I will have to teach you one more terminology here, right? Because these books, they use different terminology. They talk about the same things, but they use different words, right? So let's say that you are given a set of functional dependencies f, right? And then let's say there are and you want to infer other functional dependencies, right? So let's say if you have a implies b and b implies c, then we can infer that a also implies c. Yeah? This is coming from your transitivity rule, right? And then we have another definition called as f plus, or closure. So given an f, given a set of functional dependencies f, the set of all functional dependencies which are logically implied by f is called as closure of f, right? So this is denoted by f superscript plus sign, right? So so this is called as the closure of the functional dependencies. We'll also talk about closure for a set of attributes. That is a different thing. But here, when I'm talking about Armstrong rules, I think this terminology you should know, that what is called as the closure of functional dependencies. So closure of functional dependencies is the set of all FDs which can be logically implied from the given set F, right? So this is what is called as closure of set of functional dependencies, right? And as I said before, theoretically speaking, you can determine the closure of a set of functional dependencies using just the Armstrong axioms. Of course, you have to be very creative in using them, but nevertheless, theoretically, I am saying that you can do it. We will cover some actually algorithms which are much more simpler to grasp. But I think this is important. That's why I'm talking about this, right? So you should know this concept of Armstrong axioms. There's three simple axioms, as I covered before. Reflexivity, that means for any given sets, alpha and beta, if beta is a subset of alpha, then alpha implies beta. Then full argumentation, uh, alpha implies beta, then I can argument gamma, a set of attributes gamma on both sides, and that will still hold. And the third one is transitivity. If alpha implies beta and beta implies gamma, then alpha implies gamma, right? Okay, right. And this is that property that I was saying, that just using these three, you can determine all the FDs which are logically implied by your given set F. Okay. Okay, just a small example here. This is the reason I even changed the slides here. So let's say that you are given an relation A, B, C, C, G, H, I, right? These are the set of attributes. And let's say that, these are the set of functional dependencies, right? I think, I should, tell this, that, whenever I teach this topic, people go too much into maths and they forget what are these functional dependencies, right? So, again, I would like to again emphasize this fact that, these functional dependencies, they don't fall from the sky. They are actually written by understanding the business logic, right? So in this chapter, we don't go too much into that aspect, and we try to teach it like an algebra, but nevertheless, you should never forget the roots of these, right? So for example, in a very classical question in exam, is that I can give you a business use case, let's say railway reservation system, or maybe and student academic management system. I can give you the description, and I can ask you to actually write the functional dependencies which hold, right? So then you actually have to think about the business use cases, and all the kind of constraints which are there in your application, and then write the functional dependencies, right? So you will write functional dependencies like this, and then using these functional dependencies, the task of good schema construction comes in, right? So these are two different ways of designing schema. I'm digressing, but I want you to understand this, that you know one way of designing schemas is through ER diagrams. The second way is that you study your business logic, come up with all the functional dependencies which hold in your business logic, and then you construct the schema which is in BCNF and 3NF, right? So we'll have a perfect example of this, when I teach normalization. You'll get an example, right? So don't think that this is just theory and it has no value just because I'm just doing some algebra here. It is very well connected with the real world. Okay, yeah, sorry. Now coming back to this video, right? So you have a relation A, B, C, G, H, I, and let's say these are the set of functional dependencies which hold on that relation, right? And it's just some examples of the other FDs which can be derived out of these, right? So from this, I can derive that A implies H. And how do I do it? I think I have A implies B and B implies H in my set of F, right? So we'll do transitivity and then we'll say that A implies H is also true, right? So now let's see something little bit more interesting. Okay, so using these FDs, let's say I ask the question, does AG implies I? We'll see how we get it. So we start with the functional dependency A implies C, right? And then let's say I argument it with G on both sides. You remember the full argumentation rule? If A implies B, then I can argument anything, some set of attributes gamma on both the right and the left side, and the functional dependency still holds. So I started with AC, and I implied and I sort of attached G on both the left side and the right side of that FD, and then I have this functional dependency CG implies I, it is given, right? So now these two FDs put together, AG implies CG and CG implies I, right? You know that by transitivity AG will imply I, right? So this is how you have to use the Armstrong rules to check whether a given FD holds, and even there is an algorithm to use these Armstrong rules to compute this closure, which is the set of all logically implied FDs. We'll not cover that algorithm. We'll cover a slightly easier to understand algorithm. Okay, I think just one last example. So let's say you want to infer this CG implies HI, right? So you have CG implies H and CG implies I. By your splitting rule, by right side splitting rule, I can combine both of these and say that this holds. But just I wanted to show you that you don't even need that. You just need the Armstrong rules to get to this. So let's see how we do it. So we have CG implies I, right? And now I argument CG on both the left side and the right side of this functional dependency. Okay. Now, since CG is already there on the left side, putting one more CG over here, it does not really make sense, right? But whereas, the CG can be added on the right side. Okay, so now that gives you the from the argumentation you get CG implies CGI. Okay, and then I have this functional dependency CG implies H, which is given, and over here I again do augmentation, and I think I augment I on both the left and right sides, using that augmentation rule. And then now you see these two FDs, CG implies CG and I, and then CGI implies HI, right? So then you can put in transitivity to get CG implies HI, right? So this is what we wanted to check, right? So just some examples to show that how Armstrong rules are self-sufficient to get to check for any FD. And as I said before, there is even an algorithm to determine which can determine the closure of the given set of functional dependencies using just the Armstrong rules. But That algorithm is there in the core textbook, but we will not cover that.